Hello everybody, today we'll be doing partition list. In this problem, we are given the head of a linked list and a value of x. Partition it such that all nodes less than x comes before nodes greater than or equal to x. You should preserve the original relative order of the nodes in each of the two partitions. So what we have here is a input and an output. This is our base case, happy case. So here's what we see. We see a everything that is less than 3. We're going to move it before everything that is greater than or equal to 3. So you can see that all the items that are less than 3 have been moved to forward into this particular location. What we can do is that we can maybe get an item that is greater than any of these or lesser than any of these. So these would be edge cases, right? Edge case. So edge case is that, let's say this is 6, we don't find anything. So basically, I think we should return the same order. The same should be given if we are less than everything. What would happen if we would have an output less than everything? Let's say we have an output of 0. Let's say we don't see anything at all. We have to move anything at all, so everything less than the node of x comes before nodes greater than or equal to x. Well, all nodes are less than x, and greater than or equal to x, so nothing occurs, I don't think. With that, I think we're ready to do our match. So we're going to do a 2-pointer solution. So the reason why we chose to do a pointer solution is because what we can do with pointers is that we can build 2 lists. One list with all the items that are less than the value in relative order, and everything greater than that value or equal to that value in a separate list. And we can glue the 2 lists together later. We could use an array to hold everything, but that's just extra space, so we're just going to use the properties of the pointers. So here we go. Match plan. Create 2 dummy lists, dummy nodes, one for lesser left side and one for right side. Then go through all nodes and append to left and right side. Glue the left side to right side. And set right dot next to none. And yeah, let's return the left side, the head. That's it. That should be it. Let's implement it. All right, let's check it out right here. Give it a shot. So we have the left side and the right side. Let's just set a list node, and we'll set it at let's say LR. I think that looks good. We can make this one line. So now we have the left side and right side. We can call it left dummy and right dummy. That way it makes much sense to the next reader, because we all know what dummy means. Dummy node, left dummy node, right dummy node. Let's just left dummy, right dummy. I think that preserves our knowledge from previous reading of code, so we understand the context for what we're using these pointers as. And we have an L and an R, which is not a very value, so we know for sure the reader we'll know for sure that this is a dummy node. We will not be including this in our results. Okay. So now we have, we also want our left and right to be equal. So left and right is equal to left dummy and right dummy, so that we can move these forward. Okay, and let's set cur to head, because we want to be clear about what we're doing. We're not trying to throw away the head node. We can, but I mean, we just leave it alone, you know. But that way, people know what we're doing when we set cur, because all the time people see cur, we're seeing cur.next. That's what's happening, right? So if cur.val is less than our x, what happens here is that our left.next is equal to our cur, okay? And left equals left.next. Else, that means it's greater than or equal to. So right.next is equal to cur, and right is equal to right.next. What happens afterwards is that we're always incrementing cur. It's always going forward. Now, with this, we have gone through all the nodes and appended to the left and right side. Then we're going to glue the left to the right and then set right to be none. Okay, so to glue this, so we say, so the last item of left dot next is going to be equal to right dummy dot next. So that glues the two halves together. Okay, so let's say we have L pointing to 1, 2, 2, and then we have R pointing to 4, 3, 5, right? So what happens is that when this is dummy, the right dummy, and we point it to right.next, which is the 4, and we take the left.next, which is this last item here on the left side, as we can see from this code, and we point it directly at the 4. So now we have 1, 2, 2, 4, 3, 5, which we want to return. But there is one last thing. We want to set right.next to none, because we don't want that. It should be none already. We probably don't need this line of code. I'm going to just take it out. Maybe we got it wrong. Maybe we got it right. Who knows? But I don't think we need this line of code. With that, left.next is equal to right.dummy.node. And let's return. I think we can return now. Let's return left dummy.next, because we don't want to return the left dummy. We just want to return all of the rest of it. So let's run the code. I think we have an infinite loop somewhere. I'm not sure where. Okay, so let's see what's happening. Why do we have an infinite loop? That doesn't make any sense. Yeah, that really doesn't make any sense why we would have an infinite loop. Ah, I see. Darn, that's why. Cur equals cur.next. My bad. That is funny. Little shorthand, a little too short. Error, found a cycle in the linked list. What is the cycle? So let's see. Apparently, we do need to set right.next equals none. The reason being, it currently still points back at the 2, and we never released that. So basically, what happened was, this never released the last pointer to the 2, because it still points to 2. That's why we have a cycle. And so that's why we have to set right.next equals none. Okay, with that, we have solved this problem, and we have reviewed it. So with that, I think we're ready to evaluate the solution and finish off this problem. So evaluate. The evaluation that I have is going to be O of n. It's going to be O of n because we have to go through the whole list. Time complexity. And the O of 1 space complexity. So O of n time complexity is because of the going through entire lists once. And space complexity is because we used only a couple pointers. You used 3 pointers and made no new memory. And with that, we have completed the problem. If you enjoyed this video, like and subscribe. For more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.